Hi Mohammed, this is your feedback video for the Circular Motion 2 homework. Okay, let's start with question 1. So they want you to label the forces acting on the car in both situations. Okay, so you've labelled the reaction force correctly here and here, well done. But there's a couple of issues here. Okay, now a few people have done this. Centripetal force is not a real force. It's the kind of overall effect of all of the real forces acting on the object. It's the vector sum of all of the real forces acting on the object. It's not an actual force, okay? So we don't label it on the diagram. So you shouldn't have these in here. Let's talk about friction. Right, you got your friction arrows pointing the wrong way. Friction tries to oppose the motion of an object. Think about what would happen if this was a frictionless surface, and say this is a car going round a roundabout. The center of the roundabout's over here. The car would have a tendency to slide outwards, wouldn't it? Well, the friction is what stops it from doing that. So the friction is trying to oppose that outward sliding motion. So the friction actually acts. It actually acts that way. That way. In this diagram, it acts the opposite to how you've drawn it. It's trying to stop the car from sliding up the slope, so it acts parallel to the slope, but that way. Okay, so I'm just going to add it to this diagram because we're going to need this in a minute when we discuss it for the next bit, because I need to discuss it. So that's friction. Okay, so let's have a look at this. So state the possible origins of the centripetal force in figure 2. In other words, what are the real forces that are contributing the centripetal force that are keeping it going in a circle? The horizontal component of the weight of the car? Not really, because the weight of the car does not have a horizontal component. Look, it's vertical. There's no component acting horizontally, so that's not correct. Yeah, I kind of know what you mean. Okay, let me explain it. There are two things that are providing the centripetal force: the horizontal component of the reaction force and the horizontal component of the friction force. Okay, there's the vertical, call that theta, and let me just draw the horizontal, call that theta. R sine theta, in other words, the horizontal component of R plus the horizontal component of the friction, those two together combined are what give the centripetal force. Okay, so you need to make some adjustments here. You need to write a new answer here. Okay, this bit's good, well done. Okay, I'm going to add your marks up at the end. Right, next question. Correct. What's the centripetal force? Interestingly, yeah, that's correct. So what's gone wrong here, because that's not the right answer. How much is this? What's the mass of this thing? 150 gram, okay. Times V squared. Okay, over R. What's R? 250 mil, yeah. Yeah, that's right. I've got a feeling what you might have done is forgotten to square V, but I'm not sure, but that's not right. You need to check that again. Tension in the string. Yeah, now although that's wrong, you've done the right method, so you get an ECF mark. Okay, so yeah, just go back and check this one again, but everything else is fine there. Okay, next question. Okay, yeah, so they want you to, so this is a van going over a humpback bridge. There's a parcel resting on the floor of the van. Label the forces on the parcel, not the van. So the parcel's not moving relative to the floor of the van. It's not sliding along the floor, so there's no friction force on the parcel. There's no driving force on the parcel. There's only vertical forces acting on the parcel. Okay, so although they're right, because of these, I can't give you a mark. Yeah, this is good. Well done. Yeah, nice work. Right, what's going to happen to the magnitude of the reaction force if we increase the speed of the van? As the speed increases, the value of R would also increase. Unfortunately not, that's not true. As mg would decrease. Okay, how can mg decrease? mg is the weight of the parcel. That is a fixed number. It doesn't matter how fast the van's going, mg is not going to change. Okay, but think about it. Look at this equation that you've written here. R equals the weight of the package minus this term here. This term will increase. This term will increase if v increases. So R will decrease because you're taking away a larger number here. Okay? You need to explain that. And any value greater than 15 meters per second means that the value of R would be negative. Thus the parcel would accelerate downward. No, that's not what would happen here. I mean, you're right that R would become negative, but it doesn't mean the parcel would accelerate downward. At this particular speed, what I'd rather you said is that at this speed, R would become 0. When R is 0, the package loses contact with the floor of the van, so it would actually lift off the floor. Okay, so we can talk further about this in the lesson if you want, but yeah, you've got some amendments to make here. And then finally, this is good, well done, nice work. Unfortunately, this here is not right. Yeah, I'm not sure quite. Let me see. I'll just give you a couple of pointers about how you can do this. Basically, let me just write down the equations again for centripetal force. There's one that looks like that, and that's equivalent to this. And we can use either of these equations. Let's say we use this one. F is mr omega squared. Let F equal 60 newtons. Find what omega that corresponds to, and then once you've got omega, you can find the frequency. Okay, so have a go at doing that. Let's have a look at this one. Okay, I've just had a read through your answer. Okay, the first half of it is, unfortunately, it is a bit muddled, but you do pick up a few marks later on. So really quickly, because I'm going to go through this in the lesson. First sentence, a bit vague. Weight acts on the ball vertically downward. Okay. Third law states every action has an equal and opposite reaction. It's not really, this isn't an example of a Newton's third law pair. Okay, we'll talk about the third law in the lesson. That's the hardest thing to explain. The tension in the string acts radially outwards, away from the center of the circle. Well, I mean, if you consider the forces acting on the ball, though, the tension force, the tension in the string acts it does two things. It creates a kind of a pull force on this support here, which does act radially outward, but it also acts on the ball, and the tension force on the ball acts inward toward the center of the circle. This first bit here is a bit muddled, okay, but let's have a look at what you've done next. Newton's second law, okay, centripetal force acting radially inwards is proportional to the acceleration, okay. The ball is considered to be accelerating toward the center of the circle. Okay, here we go. Newton's first law, yeah, this is fine. The speed of the ball is constant, but the velocity isn't, yes, as the ball's direction is constantly changing, yes. Thus the ball has must have a resultant force acting on it. Right, that's pretty good. Okay, this would be worth maybe 4 marks, maybe 3 actually, because you haven't talked about why the string won't be horizontal, so I'm going to give you 3 for that. Okay, right, well, if you've got any questions, let me know and we'll talk in the lesson.